Good morning, calculus. We're going to do some more derivatives involving some trig functions, e to the x, and then just some rate of change and tangent line application problems. So, quick refresher, how do you find the equation of the tangent line? So when we find equations of a tangent line, we're looking at a specific point. And let me call that point x1, y1. You might just be given x1, but if you're given x1, you can always plug it in to find y1. And if I'm given a point, then I like to use point slope form to write the equation of the line. And then if we know the point, we also need to find the slope. And to find the slope, that's when we find the derivative at whatever that x value is. So we find the slope first and then plug it in. I'll plug in that x value. To find where horizontal tangent occurs, this is something that comes up a lot in chapter 4, but just think of some function. Maybe it's got some twist to it. The horizontal tangent line. So the tangent line is the line that just kind of grazes the function at one point. It's horizontal right when you get to kind of like these peaks and valleys. Right? If I want to find out when do I get these peaks and valleys, that's when my rate of change of my slope is 0. So that's when m is 0. And slope and the derivative are the same thing. So how do you find where you have a horizontal tangent? That's when you set the function's derivative equal to 0. So you solve this for x. So take the derivative, set it equal to 0, and solve for x. This happens a lot throughout the course. How do you find where tangent lines with other slopes occur? Well, say the slope isn't 0. Say I want to know when the slope is, I don't know, -7 or something. You just set the derivative, which is the slope, equal to the given slope. So say the given slope is m, then we just solve when does the derivative equal that given slope for x. So when it's 0, we want to find out what the horizontal tangent line, that's specifically when the slope is 0. But if the slope is 3, 4, 5, 6, 7, we want to find out those points, just set it equal to 3, 4, 5, 0 instead of 3, 4, 5, or whatever the slope is. General application problems, this is going to make more sense a little bit later, but if you're trying to find a value of a function, we just plug into the actual function to find out what the output is. But if you want to find the rate of change of something, then we plug in to the derivative. Plug into f of x. And this is going to come up in some examples a little bit later on. All right, so we're trying to find the derivatives of sine and cosine, and I'm not sure if we got to it in class or not. But you're going to need, before we do that, some information. The special limits are going to come up. And these are some trig identities. And both of these are going to be used, one for sine and one for cosine. So let me go back and start with sine. We know what the sine function is, and if I want to find the slope of it, that's equal to the limit as h approaches 0. Remember the difference quotient, f of x plus h minus f of x over h. In this case, my function is sine, so it's going to be sine of x plus h minus sine of x over h. And somehow we need to do some work to this to find the limit. And this sine of x plus h part, I can rewrite using this trig identity right here. So instead of u and v, it's going to be x plus h. So I'm going to rewrite sine of x plus h as sine of x cosine of h plus cosine of x sine of h. So we have the limit as h goes to 0 of sine of x cosine h plus cosine of x sine of h. And then we still have the minus sine of x over h. So this part right here is right here as h goes to 0. And then what I'm going to do here, because nothing seems obvious, but I'm going to switch these two terms. So this becomes sine x cosine h minus sine x plus cosine x sine h. Now these are both over h. This whole thing's over h, and that's equivalent to just breaking up into two fractions with the same denominator. And what I'm going to do next is recognize that there's a sine x in both of these terms that I can factor out. And if I factor that out, I'm left with cosine h minus 1, and this is all over h. Over here, I'm going to rewrite it slightly different. I'm going to write it as cosine x times sine h over h. So the limit as h approaches 0, I don't know if you recognize it yet, but I have a couple special limits here. This right here and this right here. So this is one of the special limits that's going to approach 0. Even if these are flip-flop, that's still the case. So this is going to go to 0, and this one is going to go to 1. So as h goes to 0, this becomes 0. And as h goes to 0, this goes to 1. Sine of x doesn't have any h in there, so x and h aren't related. So as h goes to 0, sine of x is still just sine of x. And same with cosine of x. 0 times sine of x is just 0. So cosine of x times 1 is just cosine of x. So it turns out that the derivative of sine happens to be cosine. Something to remember. And then what's the derivative of cosine is kind of the next question. And you might guess that it's sine. Maybe we did this in class already. But it's the same process. And it's if you've seen how I took the derivative of sine, try it on your own to find the derivative of cosine. And then kind of come back and finish the notes and see how it turns out if you get stuck. But cosine of this is like the limit definition of the derivative of cosine. And then cosine of x plus h, I need to use, where's the other trig identity? This one right here. So let's do this one in blue again, I guess. So cosine of, in this case, it's going to be x plus h. It's going to be cosine x, cosine h minus sine x, sine h. So we get the limit as h approaches 0 of cosine x cosine h minus sine x sine h. And that's this part right here. Minus cosine x over h. Okay. So this one actually works out almost identically to the other one. I'm going to swap these two pieces. So I'm going to get cosine x cosine h minus cosine x minus sine x sine h. And this is all over h, which is equivalent to having the two of them over h separately. And if I factor out the cosine x, I'm left with, they both have a cosine x, I'm left with cosine h minus 1 over h. And then here I have a sine h over h. And now if I take the limit as h approaches 0, this is going to approach 0, this is going to approach 1. And this is going to stay cosine x because there's no h in there, minus sine x. Now cosine x times 0 is just 0. So we're left with negative sine x. So it turns out that the derivative of cosine x is equal to negative sine x. And that is the other trig derivative to remember. I know what you're asking yourself. Mr. Florio, can we also find the derivative of tangent, cotangent, cosecant, etc.? And I'm just going to say, hold that thought. We'll get to it. And one more derivative is the derivative of e to the x. And we're not going to derive it. This is probably the best derivative ever, top 5 at least. The derivative of e to the x is, in fact, e to the x. So that sounds weird. And that's one of the special properties of e to the x, is that if you want to find the slope of e to the x, you just plug in that value into e to the x, and that gives you the slope. So easiest one to remember, or I think it's one of the easier ones forever. Like I said, top 5, not 5. Okay. I don't know if I printed these out for you in class, but if not, you're going to want to copy it down. But here's an application problem where we need to find the derivative of some sine functions to answer the questions. So the population of a group of deer living on an island with wolves can be approximated by this function right here, P of t, where t is the number of months passed since data has been recorded. One thing you might be asking yourself is, why is a deer population model involving a sine function? So the 375 is going to kind of start it up here. 250 is going to kind of be like the amplitude, so it's going to go within 250 above and 250 below that. But why would a deer population look like that? And one thing to think about is the more food, the more they populate, the more they repopulate, the higher the population is going to go. But then, as the deer population goes up, the predators of deer, like wolves, will have more food to eat. And now that they have more food to eat, they're going to start eating more deer, and then the deer population goes down. And as the wolf population goes up, the deer population goes down, until you get to a certain point where now that there's less deer and now there's less food for the wolves to eat, and now the wolf population goes down. Now that the wolf population goes down, the deer population can start going up again. Once the deer population goes up, the wolf population goes up, which causes the deer population to go down. So this is what's like a predator-prey model. And it kind of has that sort of equilibrium. So maybe that can convince you why this function couldn't model a population of deer. Anyways, if I want the population of deer after 18 months, I think one of the first things that you took notes on is, how do you find out value? I'm just going to plug it into the function. This function tells me the population. T is the number of months. So if I want the population after 18 months, it's going to be 250 times sine of 18 plus 375. And I put that in the calculator. And I'm getting, unless otherwise specified, be in radians, I get about 187 deer. So after 18 months, there's about 187 deer. But part B, what is the rate of change of the population after 18 months? So I want to know, is the population going up? Is it going down? What's going on? So if I want the rate of change, I need to find the derivative of the function after 18 months. So first, before I plug in 18, let's find the derivative. So the derivative of 250 sine of t plus 375. Well, the derivative of the 375 is just 0 because the derivative of constant is just 0. The derivative of sine is cosine. If it's being multiplied by some factor, no big deal. It's just going to be 250 times the derivative of sine, which is cosine. Let's make that green. I like making derivatives green. And now that I have my derivative function, we can plug in. So it's going to be 250 times cosine of 18. And that'll tell me the rate of change of the population. And if we toss that in a computer, I get about 165. And that number represents the amount of deer per month. It's a positive number, so it means the population is increasing at this moment. So we're kind of, we're somewhere in this part of the function where it's increasing. If it was negative, then it would be going down at that rate. Anyways, so some tangent line problems, and we may have seen these before. Find the equation of the tangent line to this given function at x equals 1. So to find the equation of the line at a given point, I'm going to use point slope form. I'm given x1. To find out what y1 is, I just need to plug that into the function. So if I plug 1 into my function, 1 squared minus 3 times 1 plus 6, I think that's going to be 4. So now we have x is 1 and y is 4. And then we just need to find the slope. So if I want to find the slope of the function, we need to find the derivative. So I need to find y prime. And this is just a nice power function. The derivative of x squared is 2x. The derivative of minus 3x is minus 3. The derivative of 6 is 0, so that's my derivative. Now I want the derivative at this point, so I plug 1 into my function. So that's 2 minus 3, which is negative 1. And that is the slope, which is going to be negative 1. And that's all the work I need. Y minus 4 equals negative 1 times x minus 1. If I want to put that in slope-intercept form, that's going to be negative x plus 1. If I add 4 to both sides, I'm going to get y equals negative x. That's a 4 plus 5. So you can be done here, put a box around it, and we're good. Or we can be done here, put a box around it, and we're good. Both of these are the same line. So we got some sort of quadratic, whatever it looks like, and at x equals 1, the slope is, apparently it's negative 1, and the equation of the tangent line is right here, negative x plus 5. So it starts at 5 and it has a slope of negative 1. Determine where the function has any horizontal tangents. So we have a cubic function. So a cubic function could look something like that, and we want to know where we have a horizontal tangent. So think where is the slope, or think where are our peaks and valleys. And it's where the slope is 0. In other words, where the derivative is 0. So right here, the tangent line would be horizontal, and right here, the tangent line would be horizontal. So that's when the slope is 0. So I need to solve the equation, when does the derivative equal 0? Well, the derivative of the function is going to be, so y prime is going to be 3x squared plus 12x plus 9, and I want to set this equal to 0. Let's see, I can divide both sides by 3. Let me see if that's what I want to do. Or you could factor out a 3. It's really the same idea, but I guess that's what I'm doing this time. So this becomes x squared plus 4x plus 3 equals 0. And this is going to factor nicely. What multiplies to 3 that adds to 4? And that's going to be 1 and 3. 1 times 3 is 3. 1 plus 3 is 4. So at x equals -1 and x equals -3, we have a horizontal tangent line. So if I were to sketch this graph a little bit better, at -1 and -3, it's a cubic and it's positive coefficient. So, it might go something like this. And I don't know exactly what's going on, but I know at -3 and at 1, we're having horizontal tangent lines. So that is where our horizontal tangents are. Determine where this function, if anywhere, has a horizontal tangent line. Not every function is going to have a peak and a valley, so we have to say if anywhere, and this function might be one of those. So we need to find out when does the derivative equal 0. Well, the derivative of 1 over x I can rewrite as x to the -1, and then the derivative is going to be a quick power rule. It's going to be -1 x to the -2. So I need to solve this. So this is equivalent to -1 over x to the +2. There is no solution to this. You can't. There is nothing I can divide -1 by to get 0. As x goes to infinity, this is going to approach 0, but I can't actually plug in infinity. So there actually is no solution to this. Determine where, if anywhere, the function has a horizontal tangent. Yeah, no. This function doesn't have any horizontal tangent lines. Which makes sense. I mean, I believe 1 over x is something like this. And there's no place where you have a peak and a valley. As x goes to infinity, it's getting close to 0. Like I said, as x gets really big, it's going to get close to 0, but never actually hits 0. Okay. Determine if the function has any horizontal tangents. So again, we want to find out when does the derivative equal 0. And now we know the derivative of e to the x. Top 5, not 5 derivatives of all time. Derivative of e to the x is just e to the x. Derivative of -2x is -2. And we're going to set that equal to 0. Add 2 to both sides. We get e to the x equals 2. And now how do I solve for x? So we need the inverse function of e to the x, which is the natural log of x. So I'm going to take the natural log of both sides. So the natural log and e to the x are inverse functions. They undo each other, and that just leaves me with x equals the natural log of 2. And that's it. If you plug the natural log of 2 into your calculator, if you're curious what that is, it's about 0.693. That's the exact answer, and then that's the approximate answer. Okay. I believe this is the last question. 2 more questions. Determine where, if anywhere, this function has a slope of 3. So instead of solving when the derivative is 0 to have a horizontal tangent, I want to know when the slope is 3. So we need to solve when does y prime equal 3. And y prime is going to be 6x squared minus 10x minus 4. And set that equal to 3. We have a quadratic. Solve it, set it equal to 0. So I'll subtract 3 on both sides. So we get 6x squared minus 10x minus 7 equals 0. We have a quadratic that's not going to be factorable. So use the quadratic formula. Now, if you have a nice graphing calculator with a program in, you can just plug in 6, -10, and -7 in, hit enter, and you're going to get x is about 2.198, or x is about -0.53. If you don't have that nice function on your calculator, then you're doing the x equals -b plus or minus the square root of b squared minus 4ac all over 2a. A is 6, b is -10, and c is -7. So you're going to get negative 10, which is really just positive 10. Plus or minus the square root of negative 10 squared minus 4 times a, which is 6, times c, which is negative 7, all over 2 times a, which is 6. And I'm not going to go any further than that. This is what you get. Where is the function of a slope of 3 at these 2 points? I don't want that in there, right here. So at y has a slope of 3. All right, last question. Determine where, if anywhere, the function has a slope of 1/2. So what we're trying to do is find out when is the slope, which is the derivative, equals 1/2. The derivative of this function, the derivative of sine is cosine. So the derivative of 2 sine x is going to be 2 cosine x. The derivative of 2x is just 2. And set that equal to 1/2. So let's solve this for x. Subtract 2 on both sides. We get 2 cosine x equals 1/2 minus 2 is going to be negative 3/2. Divide both sides by 2. Or take a half of both sides. So then we get cosine x equals negative 3 over 4. The unit circle is not going to help here. Because negative 3/4 is not on it. Right? It's not like if it was like 1/2 square root of 3 over 2, root 2 over 2 would be okay, but negative 3/4 isn't in one of those points. So I need to do the inverse function of cosine x. The inverse function of cosine x is called the inverse of cosine x. So that's going to be the inverse of cosine on both sides. Inverse function undoes the cosine function, so I get x equals whatever the inverse cosine of negative 3/4 is. And put in the calculator. Again, radians. And we get x is about 2.427. So this is the exact answer, and this is the approximate answer. That's it. All right, again, if you like the video, make sure to share, subscribe, ring the bell for notifications, and smash that like button. If you have any questions, I'd love to hear it in the comments. Thank you, and have a nice day.